Hey, what's up, guys, man? Welcome to the Flat Earth of Judah Tribe. This is your boy. Judah Tribe, man. On to this Flat Earth segment of the internet. Just doing a quick video, man, telling you about the ISS, satellites, all that stuff, that I told you on my recent channels that all got taken down. But this is an engineer. I want you to subscribe to the guy too, man. I'll leave a link at the bottom to his channel. But this guy's a real engineer, so he knows more technical stuff than I ever would know. But he's just saying that all the stuff that you see on TV, air bubbles. Look, man. As far as like them doing ISS and all that stuff, that's all done underwater, right here on Earth, man. They ain't getting past the firmament. They ain't doing anything. You can see the water bubbles and everything. And I'm sorry for all you guys who grew up in that era, seeing them supposedly going to the moon, but they faked y'all out, man. Y'all been bamboozled, y'all been hoodwinked, and y'all been faked out. And I would like for you guys, just don't be ignorant about it. Do some research on Flat Earth, and you'll see all the things that they hide from you. Why are they hiding? My guess is, they ain't no guess. It's I know that they're trying to hide the Most High and from His creation, because in order for their evolution and Big Bang and all that to work, it has to be a heliocentric world. The Earth has to be a ball. So I want you to pay attention to this man right here. He's went to college. He's got his master's, doctor, whatever, but he's an engineer and he knows what the hell he's talking about. And leave your comments at the bottom. Again, this is the Flat Earth of Judah Tribe. Deuces.
Hi, I'm Brian Mullen. This is Balls Out Physics, Episode 4, the ISS, Satellites, and the Thermosphere. When I first started researching Flat Earth theory, one of the first things I had to accept, if I was going to even think about the possibility, would be that NASA and all of the photographs or composites, as they are actually called, or in video, whatever you want to call it, from space is fake. And I mean, that's a giant leap you have to take to accept something like this, or to even consider it. And so I started watching videos that people had produced showing that the ISS was a hoax, and that satellites were fake. A lot of people, there were videos showing that on spacewalks, when it looked like they were on space, people caught a bubble rising from an astronaut's helmet, or a guy with a scuba tank inside the ISS in a window, and just other things like that. And so I first started seeing that stuff, and it was pretty convincing, but at the same time, I thought, well, it's not definitive proof, because how do I know that this stuff hasn't been edited in to sway opinions, because there are people out there that believe the Earth is flat, and they want everybody else to believe it too. So I remained skeptical, but I also was doing my own little experiments on Earth with binoculars and just seeing how far I could see over the horizon, and drawing distances in AutoCAD and doing calculations and finding that I was able to see things much farther away, and observing the sun and the moon and the stars and things like that. And so my opinion started to sway a little bit, but I still was trying to prove it wrong. But I'll never forget the moment that everything clicked. And that was on a Friday night. I was just watching videos, doing my typical thing, just wondering, trying to prove these things wrong that I was seeing. And I don't remember what video it was, but the narrator in the video said, how are there satellites and a space station in the thermosphere layer of the atmosphere when the temperature gets up to 2,000 degrees Celsius? And that's when everything clicked. I remembered, oh wow, I remembered from astronomy, my professor talking about the temperature in the thermosphere. And I remember her taking a marker like this and holding it out, and held it in front of the class like this, and she said, the temperature in the thermosphere layer of the atmosphere is upwards of 2,000 degrees Celsius, or can get up to upwards of 2,000 degrees Celsius. But you can't actually measure the temperature, because the gas particles in the thermosphere are spread so far apart that there are not enough of the particles collide with the tip of the thermometer to make it show a hot temperature. because heat is actually kinetic energy. And a thermometer works by measuring basically the collisions, the energy being transferred to it, and that's why it shows you what the actual temperature of the liquid or the air or whatever is. And so I remember sitting in class and thinking to myself, well, how did they measure the temperature in the first place? How do we know it's 2,000 degrees Celsius if you can't measure it? And I thought about maybe thermal imaging or something, but still you have to be measuring that kinetic energy. So it didn't make sense to me. But at the time, I didn't put two and two together and realize that that's where the majority of LEO, which are low Earth orbit satellites, and the International Space Station and the Space Shuttle used to be. You know, what they used to, or the Space Shuttle used to be, but everything else orbits the Earth. And so when that hit me, I said, wait a second, this can't be. And I thought about the thermometer. I really started to think about thermodynamics. And I had to take thermodynamics to get my engineering degree, and so I went and I pulled out my thermodynamics book. I actually kept all my books. I didn't know I'd be using them for something like this later in life, but I knew I wanted to have them for reference. And so I got my thermodynamics book out, and I went to the first law because I remembered what the second law was, but I wanted to read them both again. So when you go and you read the first law of thermodynamics per this book, says, the first law of thermodynamics is simply an expression of the conservation of energy principle, and it asserts that energy is a thermodynamic property. And that's basically, you know, more complicating way of saying what I just said, that heat is energy, kinetic energy. Okay? And the second law of thermodynamics asserts that energy has quality as well as quantity. And actual processes occur in the direction of decreasing quality of energy. And what that means in terms of heat is that heat, something that's hot will move to a colder area, because the energy in something that's hot is higher than the energy in something that is cold. So they give an example, and they say, for example, a cup of hot coffee left on a table eventually cools, but a cup of cool coffee in the same room never gets hot by itself. The high temperature of energy of the coffee is degraded. It's transformed into a less useful form at a lower temperature once it's transferred to the surrounding air. So they give a little picture, or they show a little picture of this. I mean, you can probably imagine a cup of coffee cooling down, but they show that, you know, if the cup of coffee is 70 degrees Celsius and the surrounding environment is 20 degrees Celsius, eventually the heat will dissipate from the coffee and become the same temperature as the room around it, or the area around it. I mean, this is common sense. Everyone knows this, that if you leave something out that's hot, soup or whatever, and you don't consume it in time, it's eventually just going to be room temperature, and it may not be as enjoyable. So keeping that in mind, hot goes to cold. Now, before I took thermodynamics, I actually knew this pretty well because my dad is a mechanical engineer, and he basically groomed me to be an engineer from birth because that's what he is and that's what he knows. And he told me hot goes to cold. He wanted me to know that. It was something he was adamant about. But the way I really learned it is whenever I would leave the back door open in the summertime, he would say, "Brian, shut the back door. You're letting the heat in." But in the wintertime, it was, "Brian, shut the back door. You're letting the heat out." He always said it right. He always said that the hot goes to the cold. And so that was always ingrained in my head. And then when I took thermodynamics, I actually found the class very interesting because it built off of that basic principle that hot goes to cold. So why this all clicked for me, and you may or may not agree with this, is that I don't understand how this heat is not being transferred to the International Space Station and all the satellites up there. But so first, let's look at how the atmosphere is constructed, or the layers of our air exist above us. If you go to Google Images or Google Images, or just get on Google and type in layers of the atmosphere or temperature, you might find this chart. I found this one. I decided to print this one out because it was the most clear. They vary with elevations and where the delineation lines are, but I'm just going to use this one to explain this. Okay, so basically there's 5 layers of the atmosphere or of our air, And we are in the troposphere. You might remember this from general science in middle school, or whenever you took something like that. And when you go up in elevation in the troposphere, the temperature decreases. If you ever, if you go up in the mountains, it starts to get cool. You might have experienced this. I mean, it's very common knowledge that as you go up into the mountains, the temperature gets cooler, and that always seems kind of strange, right? Because you're getting closer to the sun. But there's reasons for it. I'm not going to get into that in this video, but the temperature gets colder and colder, down to around negative 50 degrees Celsius at about 10 kilometers over here. And then you get into the stratosphere, and temperature actually starts to increase a little bit, which I always found kind of strange that it goes back up, and up to about 50 kilometers. And then you get to the mesosphere, and then the temperature starts to decrease again as you get into the next layer, and it gets down to about minus 100 degrees Celsius, which is about 100 degrees less than the freezing point of water. And then when you cross into the thermosphere, though, the temperature starts to slightly increase from about 90 to 100 kilometers based on this chart, and then it rapidly increases. I mean, it shoots up over 20, 30 kilometers. I mean, from negative 50, negative 100 degrees up to about 500, 1500 per this chart. Some say 2000 degrees Celsius, some say 2500 degrees. There's all kinds of numbers out there, but everybody can agree that it's really, really hot. 2000 degrees Celsius is very hot. To take this into consideration, or to put it in perspective, I mean, the melting point of aluminum is 660 degrees Celsius. And satellites and the ISS are definitely going to have a lot of aluminum on them. They're also going to have a lot of plastic on them for circuitry, circuit boards, and things like that. And plastic melts at around the boiling temperature of water, which is about 100 degrees Celsius. So keep that in mind. So you see the temperature keeps going up into the exosphere, and it keeps going up and up and up off the chart. And the exosphere is basically the last layer of the atmosphere, where the gas thins out so much that eventually you get to a point where there's no more gas and you're in space. And this is what I was taught in astronomy, and this is the general idea. I don't know if I said it exactly right, but that's the accepted theory. Okay? So those are the layers of the atmosphere. But I wanted to focus on the thermosphere because that's where the majority of LEO satellites are. The ISS is considered a satellite since it orbits the Earth, as is the Moon, and in mainstream astronomy. And so I drew here the thermosphere on the board, and I chose to say it starts at 100 kilometers because there's other charts out there that show 100, and it's just easier to use 100. And I also said that the top of it is at 600 kilometers because there are other charts that show it at 600. And NASA tells us that the Hubble, Fermi, and Spitzer, Hubble being the most famous telescopes, are around 560 kilometers, and they say that they're in the thermosphere. So that's why I chose 600. And these red dots on the board are supposed to represent the air. The gas particles, which basically the atmosphere up there, okay, and red because they're hot, and I've also got the ISS and satellites up there, and down here I've got the lowest LEO, which is supposed to be around 160 kilometers, and there's supposed to be thousands of satellites out there, so there's not just one down there, there's multiple, but this is just a representation, obviously not the scale. And so when you start to think about how heat works, heat and pressure works, if you, or gas works, think about a pot to visualize the air in the atmosphere. You think about a pot on the stove. You fill it with water, put it on the stove. You say you want to boil some water. Put it on the stove, and you turn the temperature on high. Okay? And eventually, about 5-10 minutes, you've got boiling water, and sometimes, the top will start to rattle around depending on how much water and air you have in there, what the ratio is. The top will start to rattle around, and it can even blow off. And that's because pressure and temperature are proportional. This is one of the things I found most interesting in thermodynamics, and one of the things you learn. As you increase temperature of a gas or a liquid, it wants to expand. And if you have it contained in a vessel like this, the pressure will increase because the particles are all bouncing off of each other, and it's trying to move out away. So I tried to illustrate this, that at the lower temperatures of the thermosphere, the air is going to be more dense. If you see I've got more dots down here, than I do up here, because the gas starts to try to expand away from each other because it's hot. The hotter it gets, the more the particles want to get away. Okay, but the particles are so far apart where all these satellites are that there's not enough of them colliding with the satellites and the ISS and everything to make them melt. That's basically what my astronomy professor said with the thermometer example, and this is the general accepted excuse or reason for why these satellites aren't melting and why astronauts aren't burning up, and that's it. Okay, and so it kind of makes sense. Someone pointed out on my channel, it made a pretty good comment. He said, well, what if it's like an oven? You know, when an oven's hot, you put your hand in the oven, and your hand doesn't burn up immediately. You can put your hands into the oven because the air is pretty spread out. You know, but if you keep your hands in there, eventually they will start to cook. Okay, and I thought that was a good example, and it made me really start thinking about this. And I thought, well, if something's hot, to keep it hot with a surrounding cooler environment, you have to keep putting heat into it or energy into it to keep it hot. So going back to the pot example, the pot's on the stove, the lid's rattling around. You say, oh, the lid's going to blow off, so you turn the temperature. You just turn the dial off, turn the heat off right away, and usually the lid stops bouncing around pretty quick, and the pot and everything cools down pretty fast because the room temperature air around is so much lower. And that gets into potential difference. The lower the temperature, the more mass around something that's hot, the quicker the temperature can dissipate to the surrounding environment. Okay, so I started thinking about the thermosphere in this sense, and all these red particles, or these gas particles, the red dots representing them. Something's got to keep them hot, right? Because space is supposed to be cold, very cold, because there's nothing out there. And the mesosphere below the thermosphere is also minus 100 degrees Celsius. If you can see down here, I drew a bunch of blue dots and tried to show them very dense because the temperature's cold, so they're closer together. Okay? And another thing I wanted to point out, this kind of a side note, is that when you heat things, every material expands when you heat it. All materials expand. And if you remember solid, liquid, gas from basic science courses, they talk about generally liquids become gases as you heat them, and so all materials expand as you heat them and contract when you cool them. But there is one material that does something different when it's cooled, and that's water. Water, when you heat it, it expands, just like in the example with the boiling pot, becomes steam, and the hotter the steam gets, the more it wants to expand. I think there might be a plateau, though. I can't remember. I've got to get back into that. But it does expand. And when you cool it, and it goes to its liquid form, it cools and cools and cools down to the boiling point of water is 100 degrees Celsius, and the freezing point is 0 degrees Celsius. And water actually gets its most dense in its liquid form at about 3 or 4 degrees Celsius. There's been experiments and research on this. I'm not sure what the exact temperature is, but somewhere around 3 or 4 degrees Celsius, water is actually its most dense in its liquid form. And then when it freezes, something amazing happens, I think. It suddenly expands. All the particles fly away from each other and they freeze. I mean, they don't stop moving. They're still moving. I mean, solids still have particles moving in them, or atoms, molecules, whatever you want to call it. But the water freezes and becomes less dense, and that's why it floats, because it's less dense than the water. That's pretty amazing when you think about it. I mean, water makes up our bodies, and 75% of the Earth, 75% of our bodies, 90%, and some people say. I mean, it varies, and it's the life giver, in my opinion, of all materials. I mean, we have to have water, and it does this amazing thing that nothing else does. I'm getting a little off track there, but I think that's a very interesting side note and something to keep in mind when you're thinking about things heating and cooling. Okay, but back to the thermosphere. Okay, there's gas here, and there's air in the thermosphere, represented by these particles, and they're hot, really hot. As you get up to the top, they get around 1,500, 2,500 degrees Celsius, as I've written up here, and they get into the exosphere. The air particles are still hot, but they're very far, they're spread apart, and not enough of them are colliding with the objects that are up there. So that's why we're told that they don't burn up. Well, something's got to be keeping the thermosphere hot. And what is that? Well, obviously it's the sun, because that's what's supposed to warm the Earth. But that's also kind of questionable, because the reason that heat isn't transferred to the satellites is because the air particles are too far apart. Well, in space, there's supposed to be no air, no gas particles. Okay, I had to cut. But there's no air in space, right? And so keeping this in mind, with the particles being too far apart to transfer heat to the satellites in the space station, how does heat from a sun that's 93 million miles away travel through the vacuum of space to get to Earth and warm the Earth? That was always a big question for me, and it doesn't make a lot of sense. But it is accepted that electromagnetic waves can pass through space or through a vacuum. Okay? And light in astronomy, that term covers the whole electromagnetic spectrum. And to give you an idea from my astronomy book, here's the electromagnetic spectrum up here at the top. And you can see it's made up of visible light, which is the rainbow in the center, and that's a very, very small portion of the spectrum. And then there's ultraviolet, infrared, X-rays, gamma rays, and radio waves, of course. And radio waves need to be able to travel through space for NASA to communicate with the space station, right? Or with the space station and Apollo missions, whatever. That has to be true for communication to be true. And so, to get an idea, of how this would warm the Earth, in my book there's another image that shows. I'll turn it this way. How much of light or the electromagnetic spectrum gets to Earth. And as you can see, only visible, a little bit of ultraviolet, and radio waves can get to Earth through the atmosphere. So by that logic, you would assume that with the atmosphere absorbing the gamma, X-ray, ultraviolet light, that's what's heating the atmosphere. That's what the particles are absorbing and warming, and that's what we're told. That these particles absorb that light, and that's what makes them warm. Okay, that's how they stay warm. Now, as I said before, you have to keep heating the system for it to stay hot, or the heat's going to try to dissipate and go into the mesosphere or to space. Right? Well, how come the electromagnetic waves or light that's hitting these satellites isn't heating them up? They're there too. Something else to consider is if you've ever seen the movie Apollo 13, to kind of get on a side note, but this is related. In the movie Apollo 13, they don't make it to the moon, and they have a malfunction, and the whole movie is about trying to get them back to Earth, and supposedly this is a true story. Well, in the movie, on the way back, they're running low on battery power, and to conserve energy, they turn off the heater, and then all of the astronauts get very cold. Well, if you think about that, if the spaceship or the Apollo 13 ship is between the moon and the Earth, it's being bombarded by light. It's not shielded by an atmosphere or anything. So wouldn't it be really, really hot? Well, I guess since these things don't get hot, same logic. But then also, how does it get cold? It's a two-way street. If there's no air out there for the heat to radiate into, to move through conduction or convection, how does heat leave the Apollo 13, right? How did it get cold? It's got to have something to move through. Only light can transfer energy through space, as we're told. On Earth, you have to have some kind of medium for it to travel through. This is common accepted truth. The heat has to move through something unless it's light. And so the same thing goes for the space station. How does heat that builds up inside the space station get out? Right? Inside the space station you have astronauts, which the temperature of a human being is 98.6 degrees Fahrenheit, which is warm. I'm familiar with that scale, living in the United States. And that's pretty warm. I mean, that's actually hot. If it was 98.6 degrees in this room, I would be sweating, and so would the astronauts. And then you have electrical current flowing through wiring. Anytime electrons flow through anything that generates heat, and all kinds of systems on the space station. How does the heat get out of the station if there's nothing to dissipate it through? Right? There's no collision. There's not enough collisions with these particles to transfer heat into the station. So how does that heat get out? It would be really warm, if not hot, inside the station. And then, when you think about it, that means that there's some kind of barrier here. Around the station that doesn't allow. I mean, basically, invisible barrier is formed. There isn't a barrier there. An actual, a theoretical, imaginary barrier is there that doesn't allow heat in or out because it's a two-way street, like I said. So, how does this work? They have to have a set temperature before they even get into the thermosphere. There has to be a nice, room temperature in the United States is usually 72 degrees Fahrenheit. I mean, and they look like they're in an environment like that when they're on the space station wearing collared shirts and pants. Most of them, they probably want something that's comfortable so they're not sweating, and they look fairly comfortable. So how do they set that temperature? Heat can't go in or out. So going back to the electromagnetic waves and light is hitting these satellites, but they don't get hot. But if these gas particles absorb light and energy and get warm, these satellites are made of metals and very dense matter, and they're cool. They're going to absorb that light too. How do they not absorb the light? How does it choose to only warm the atmosphere but not the satellites? And not the Apollo spacecraft, or not any of the probes that have been out in space that are getting hit by direct sunlight? It doesn't add up to me. It defies logic. And another thing to think about is these black lines here are supposed to represent the solar panels on the ISS. You can look up an image of it on Google if you want to see it. I didn't draw a perfect picture of it, but that's generally what it looks like. Solar panels absorb light to create electricity. And, if the temperature gets up to 1500 to 2500 degrees Celsius up here, let's say it's 1500 as I've got over here. I'm just taking approximate temperatures based on that chart I showed at this elevation. I've got 1000 down here for the LEOs. Those solar panels absorb electricity, or absorb light to make electricity, and they can work in 1500 degrees Celsius temperatures. That's very, very hot. And okay, let's say they can, and they're getting hot and they're connected to the station. Shouldn't they be transferring heat into the station? I mean, through the matter that they're connected with. I've heard people say that the satellites and the ISS have like a reflective material on them that reflects the light. Okay, but that would work for the station. But what about the solar panels? They are absorbing the heat, and the heat. If you hold a steel rod and you light a fire under one end of it, eventually the heat will travel through to the colder end of the steel rod on the other side. Metals conduct heat. I mean, basically all matter does. So heat will distribute itself through all matter. Hot goes to cold. It'll go to the colder pieces of matter. So how does this work? And if there is really a reflective material that can then reflect the light back off of you, I want clothes made out of that for an August day in Florida, because when the sun is on you in August and early September in Florida, it is miserable here. It is very, very hot, and it's humid. Yes, the ambient temperature around me is also warming me, but when I go in the shade, it's cooler. So if you can get this reflective material, I really want some. I want a hat made out of it, everything. Of course, they'd probably say it's very expensive. So this, in my opinion, defies the second law of thermodynamics. And we write laws. Science says something's a law. I don't agree with this, but we basically say that nature has to follow that law all the time. I think that's a little arrogant for us to do, but that can be seen in the whole theory of dark matter. That dark matter is theorized because galaxies appear to spin so fast that there's not enough mass in them that defies the law of conservation of angular momentum. So we have to theorize that there's dark matter to obey our laws of science. But this is disobeying the second law of thermodynamics. So we're contradicting our methods of analysis here and acceptance. So I can't believe that these things are here. I can't believe that any spacecraft have gone to the moon because they would get hot based on how all of this is supposed to work. And so I'm sure scientists and engineers have thought about these things before, and I did before I even started to question it not being real. But when you see a picture of these things, animations, really, because there are no real pictures of satellites, you can look this up, they're all CGI, they're all animations for some reason. Where you see astronauts on a space station or out on a spacewalk, you think it's there. So all these questions about the physics go right out the window. I mean, at least they did for me. But then when I say, well, wait a second, what if they're faking it? Then all of this comes roaring back. And you put the two together, and it really starts to seem like we're being lied to here. And I have to admit, it broke my heart when I realized all this, when all this clicked for me. You know, I don't want to believe that this isn't there. I used to be such a space nerd, and I went and saw The Martian actually after I filmed my last Balls Out Physics series, and I got really depressed after I watched it, to be honest. Within the first hour of the movie, I was sad. I missed the idea of humanity getting off of Earth and exploring the stars, but logic, I'm not going to let my emotions overpower my logic, because then I'm just lying to myself. And that's just silly. And I really hope that most people out there aren't doing that, because logic, we need to use logic here. And so go check out these hoax videos. Go think about things like when they're out on a spacewalk, they are always looking at Earth. They never have any equipment on the other side of the space station looking out into the great void of space. Well, people say that's because you can't film the fourth wall, or because, I mean, that would be hard to fake, I think, too. And then there's other things like, you know, the inside shots when they're showing the astronauts. People point out that they look like they're harnessed, and if you think about it, you could fit every inside shot of the ISS we've seen could fit inside a 767 or 777. So you could use a combination of harnesses and a zero-G plane. Diving and climbing at the right angles to create the zero-G effect, because you can buy tickets to go on a zero-G plane, and I mean it's expensive, but you can do it and experience weightlessness. And we have videos from the inside of those planes, and those are a good thing to watch and to compare to some of the footage we see from live interviews with astronauts. Apparently Scott Kelly allegedly just returned from space after almost a year up there. And one thing I notice about him when he does his live interviews, or when he was allegedly on the space station, is that he always liked to end his interview with a backflip or a front flip, you know, to show off that he's in space. But he's bald, and when he did that, notice his face and his head get red. Well, he's supposed to be in space. He's supposed to be weightless. So when he turns upside down, it seems like the blood is rushing to his head like it would on Earth. I don't think that should happen in space, because unless you consider maybe centrifugal forces are doing that, and going back into episode 3, if you watch that, where you know there's a force pulling towards the center of a circle in rotation, but that's supposed to be balanced in space, which I'll go back and make a sub video to episode 3 to explain that. But it doesn't add up. It really doesn't. So I don't know what to conclude. I cannot believe that they're in space. I think after all of this that all space agencies have been lying to us. It breaks my heart, like I said, but I mean it's pretty obvious to me that it's all been faked, and that means a lot of countries are in on this. And a lot of people say, well, that's too big of a conspiracy. It can't exist. Well, just because something seems too big, just saying it's too big does not disprove all of the evidence that points to the fact that it is actually happening. And something else to consider is that every single country that has a space program also has a privately owned central bank. And governments, the media, and our education systems, in my opinion, do a very good job of keeping that information from us, that central banks are privately owned by big banks. And so most people don't know that. That's a huge deal, in my opinion. It's really not that far-fetched to me. I mean, the amount of lies I've seen from governments and media in my lifetime, it just doesn't add up. So think about this one. Think about this being real or not. Ask yourself, do you really think they're up there? Go watch ISS footage. Go look at pictures of satellites. Ask yourself why when they're out on spacewalks, they never see the thousands of satellites that are supposed to be up there. You never see one go whizzing by. Or why they never, when they're inside the station, they don't show off more and show us the void of space from inside the station with a camera looking out. There's just not enough. I don't see enough to believe it's true, and then the physics is defied. So whether the Earth is flat or a sphere or concave, I don't know that really at the moment. I'm still working on that. I don't know if we have a working model of our world at all, but I know for sure that space, that men in space, human beings in space, is a lie. I don't think they've ever been there. And you may disagree with me, and that's fine, but make sure you prove it to yourself that they are there or they aren't there. Okay? Like I said, I don't want to believe it, but I have to follow logic. So, until next time, let's keep pushing for truth on this. And, well, one more thing I want to say is last year NASA's budget was over $19 billion. Until we get some really good answers to these questions, I don't think we should be giving them that much money every year. And with $19 billion, you could easily fake this. It would be a lot easier it would be a lot more cost effective to fake this and have a lot more money left over than it would be to actually do it. So, until next time, think about all this. Peace.